All right, we're learning about the history of atomic theory. For a long time, probably as long as humans have been around, we have been trying to figure out what makes up matter. And there has been this idea that matter is made of particles, and there have been people who have been suggesting it since as far back as 400 BCE, which is a long time ago, okay? However, there were other competing theories. There were some people who said, no, matter doesn't have a basic particle. You can keep dividing matter until it's smaller and smaller and smaller. You're never going to get to what is a basic particle, okay? It wasn't until the late 1700s that we started to make any real progress towards defining what matter is. In the 1700s, most people agreed that elements were substances that could not be broken down further by ordinary chemical means. They had these pure substances, and they found that they couldn't break these pure substances down into other things. They could maybe cut them up and make them smaller, but they couldn't make it into something else by breaking it down any further. And they assumed that these elements, when combined, made compounds that were different physically and chemically than the elements that made them up. They could observe that, right? They could combine things and observe that they made something new that was different. However, they didn't really understand how those elements combined. We call it chemical reactions now, and we have a pretty decent understanding of how and why it happens, but they didn't really have that understanding. They just knew, when I do this, this happens, but I can't tell you why, and they didn't know why some reactions required heat and some didn't. They didn't understand why you could combine certain elements and they would make something new, but you could combine different elements and they wouldn't combine and they wouldn't make something new. So they knew that it happened, but they didn't really understand the how behind it. In the 1790s, two things happened that made it much easier for us to understand matter. The first thing is that people started to record quantitative data of chemical reactions. So they stopped going, what does it look like when it combines? And they started trying to describe it with numbers. Did the mass change? Did the temperature change? What numerical quantitative data can we take? And when you start to gather numbers in science, you start to get answers. And the second thing, equally important, I would say, is that our technology improved. The balances that they were using were made to be more precise, so you could measure things with smaller masses, which meant when we were trying to measure the masses of elements and compounds that we were combining, we were able to measure smaller amounts, and we were able to measure them with more precision, so more information from it. The same really holds true in current science. As our technology improves, so does our understanding of concepts. As a result of these two things, they discovered some important laws. Okay, laws are what happens when we have a theory that over and over and over comes up being supported by the data. So remember, when we have a hypothesis that's supported over and over, that hypothesis turns into a theory. Well, the longer that theory hangs around and evidence continues to support it, sometimes that can turn into a law. And typically laws also have some numerical values that go with them, but in general, it's something that is very supported. So at this point in time, they may not have called it a law, but now we do, because these laws still hold up today. The first of those is the law of conservation of mass. We discussed this a little bit when we were doing chemical and physical changes, because we discussed that when you are doing a chemical reaction, you are not creating or destroying any mass. The law of conservation of mass states mass is neither created nor destroyed during ordinary chemical reactions or physical changes. So We're not creating or destroying anything. An example of this can be seen if we split one molecule of calcium carbonate and we use a chemical reaction to break it down into the things that it's made up of. The resulting reaction looks like this. Calcium carbonate becomes a molecule of calcium monoxide and a molecule of carbon dioxide. Quick refresher on how to read these chemical formulas. When we write chemical formulas like this, we use the chemical symbol from the periodic table. So Ca means calcium, C means carbon, O means oxygen. If there are no numbers in a subscript by that symbol, that means there is only one atom of that element in this compound. If, however, like on the oxygen, there is a subscript number, that's just telling you how many atoms of that element are in the compound. So in this compound, we have 1 calcium atom, 1 carbon atom, and 3 oxygen atoms. And I want you to notice that when it breaks down into calcium monoxide and carbon dioxide, we're left still, we have 1 calcium atom, and we have 1 carbon atom, and then the oxygen atoms, there's still 3 of them, they're just split up differently, right? Instead of all being attached to the carbon, 2 of them are now attached to the carbon, and then 1 of them is attached to the calcium, and they're separate compounds now. They're not all together anymore. So we broke this down. There's new substances. These would not look the same as calcium carbonate. They would have different chemical properties, different physical properties, but we didn't create any new atoms, right? We still have the same number of atoms on both sides of this equation. So the mass is going to be the same on both sides of the equation. If you were able to capture everything and weigh everything, the mass would not have changed. That covers the law of conservation of mass. Let's move on to the law of definite proportions. This says that a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. So it doesn't matter where it comes from, how it was made. If it is this compound, the composition will be the same by mass every time. What does this mean practically? Well, it means that table salt is made up of sodium, and it's made up of chlorine, and its mass is always 39.34% sodium and 60.66% chlorine. So it doesn't matter if I got this table salt out of a mine or if I made it in a lab. It doesn't matter if I have 30 kilograms of salt or 3 grams of salt. The percentage of the mass that comes from sodium is always going to be 39.34%, and the percentage of mass that comes from chlorine is always going to be 60.66%. Always. Doesn't change, no matter where you get it from or how much of it you have. And as we're going to discover as we move forward, this is true because 1 molecule of sodium chloride, which is table salt, always has 1 atom of sodium and 1 atom of chlorine in it. And because chlorine is a heavier atom, more of the mass is composed of chlorine than it is of sodium. All right, let's do the most difficult, in my opinion, to conceptualize in your brain, the law of multiple proportions. If 2 or more different compounds are composed of the same 2 elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. Is a long, run-on sentence that doesn't make a lot of sense to your brain, I'm assuming. It didn't make a lot of sense to mine the first time I read it either. So, let's look at an example. So, our example, carbon and oxygen can form 2 different compounds. They can form carbon monoxide, which is one carbon with one oxygen, or they can form carbon dioxide, which is one carbon with two oxygen. So what we notice is that these two compounds are different, and they would notice that different amounts of oxygen could react with carbon. So they set up this experiment, and in order to make this experiment controlled, what they did is they limited the amount of carbon that they were reacting to just 1 gram. Why limit it? So that you know that it's not the amount of carbon changing that's changing how much oxygen reacts with it. They want to keep the amount of carbon the same so that they can see what different amounts will react with it. And when they did this experiment, they found that sometimes 1.33 grams of oxygen reacted to make a new compound, and when they did, the compound that they got was carbon monoxide. But if 2.66 grams of oxygen reacted with it, it would instead make carbon dioxide. And if you take those two masses, 1.33 and 2.66, and you make a ratio out of them, so you divide one by the other, what you'll see is that that ratio is 2 to 1. It's not some complex number, it's simple whole numbers. And as we learn about Dalton's theory, we're going to circle back to why that is the case. But before we do that, we're going to do a small check for understanding. So what I would like you to do is I'm going to give you 3 note cards, and on the front you're going to write the 3 laws, the names of the 3 laws that we just learned. Then you're going to flip it to the back, and I'm going to set a 5-minute timer, and you're going to write the definition of that law in your words, how you understand it. Then, when the 5 minutes is up and we've finished writing, you're going to pair up with a partner, and you're going to hold up the card with the definition side out, and they're going to see if they can identify which of the laws that is. This way, we start to see other people's interpretations of the law, so we can check in and see if that helps click anything in our own brains. Okay? We have some good creative definitions out there, okay? Now we're going to dig into Dalton's law, and Dalton's law helps explain some of these, so hopefully it will help clear up some things if there's still any confusion left. Okay? In 1808, we had an English school teacher whose name was John Dalton, and he proposed a theory that helped explain those 3 laws that we just discussed. His theory, which I have broken down with the help of your book into 5 parts, is this. The first part, he said all matter is composed of extremely small particles, which he called atoms. So he's saying you can break matter down to a certain point, but then you're going to hit atoms, and it doesn't break down further than that. He said if the atoms are all of the same element, then all of those atoms will be the same. They'll have the same size, they'll have the same mass, and they'll have other properties in common. But if the atoms are of different elements, then those atoms will have a different size, a different mass, different properties. He proposed the idea that atoms cannot be subdivided, which means you can't break atoms down into any smaller pieces, and he also suggested that they cannot be created or destroyed. He said that atoms of different elements could be combined in simple whole number ratios, so that means like 1 atom with 2 atoms of something, to form chemical compounds. And he said that in chemical reactions, what we're doing is separating, combining, and rearranging atoms, not creating new ones and destroying old ones. That 5th point, right, that we're just combining and rearranging atoms, helps to explain the law of conservation of mass. If you're only separating atoms and recombining them in new ways and nothing is being created or destroyed, then there's no chance for you to lose any mass. You have the same atoms at the beginning that you do at the end, so your mass is the same. Point 4 is the one that helps explain why the law of definite proportions is true. Okay? If compounds are made up of whole number atoms, then their masses explain the ratios in compounds' weights, because you can't just add half of an atom to something. So you can't have half of its weight added to something. So I'm really briefly going to run back to the example that we did earlier and discuss this at what it looks like. If we look up here, if we're limiting the amount of carbon, the reason that the mass of oxygen required to make CO2 is double what is required to make CO is because there's twice as much oxygen in it, right? So that's why those masses form a simple whole number ratio, because that whole number ratio is simply telling you how many atoms of it there are in it. Okay? The main point that we want to drive home here with the law of definite proportions and this point of his theory is that when we are combining atoms, we're combining whole amounts of atoms. That's all there is to it. And sometimes atoms can combine in different amounts, like carbon monoxide and carbon dioxide, to make two different compounds. And as we learn more about valence electrons and covalent and ionic bonding, we'll start to understand why they form two different compounds. But that's for later on. For right now, all we have to understand is they combine in simple whole number ratios. You're not going to have one carbon atom with half an oxygen atom. It's always going to be whole numbers, and that they can combine in different forms. Lastly, we need to talk about the fact that while Dalton was miles ahead of lots of his peers, there are still a couple of things he got wrong, which are mostly the result of the fact that he didn't have the technology for this. Okay? The first one is that we have since then discovered protons, neutrons, electrons, and quarks, all of which are subatomic particles. Sub meaning a level of classification underneath. So subatomic particles are particles that make up an atom. So we have discovered that his third point, that atoms cannot be divided, is incorrect. We can break atoms down into smaller parts. Okay? They can be broken down into protons and neutrons and electrons, and those things can be broken down into quarks. So they can be divided. And you're going to learn later on in this chapter in section 3 that sometimes atoms that are the same element can have a different mass. So that portion of his second point was incorrect. They do usually have the same size and the same properties, but he was incorrect that they have the same mass all the time. Okay? All right, that is where our notes end for today.